Hi, good morning. Last class we have discussed about compact operators in L2. Okay, hope everything is clear. Today we are going to start our next section, section 4.6, and that deals with different convergence in Lx. Now what do you mean by Lx? L of x to y is set of all bounded linear map from x to y. Now L of x means set of all bounded linear operator from x to x. Okay, and in today's class we are discussing different types of convergence in Lx. Okay, we have Lx. Lx is equal to actually a set of L of x to x. Okay, this consists of set of all bounded linear map from x to x. And here convergence, here for any operator, let an be a sequence, an belongs to Lx, and we call some an converges to a. Okay, usually we call an converges to a like this. Okay, if norm of an minus a tends to 0 as n tends to infinity. This is what our definition of convergence, and this convergence is called norm convergence or uniform convergence. So first type of convergence is norm convergence. Or uniform convergence. So in this case, here we are denoting an converges to a, and the meaning is norm of an minus a tends to 0 as n tends to infinity. This is our definition of convergence. Okay, so this is called norm convergence or uniform convergence, and this is norm of an minus a tends to 0 as n tends to infinity, and we write like this. Okay. We have a result, let x can by be normed spaces, then and suppose y is a Banach space, then L of xy, this is a Banach space. So here also if x is a Banach space, then L of x is a Banach space, L of x is complete. Okay. Okay. Now suppose an converges to a. Let an be a Cauchy sequence. Let an be a Cauchy sequence in Lx, and an converges to a. Okay. This implies a belongs to Lx. Okay, therefore, as Lx is complete, if an is any sequence of Cauchy sequence of bounded operator, then a is also a bounded operator. Okay. Now the next type of convergence is strong convergence. Okay. Now strong convergence, in this case we denote. In this case, if suppose an is a sequence in Lx, belongs to Lx, and we call an converges strongly to a if anx converges to ax. If anx converges to ax. Okay, and in this case we denote as an converges to a strongly. Okay, the notation is an converges to a strongly. Okay, so the next definition is the sequence an is Cauchy in strong sense if for all x belongs to x, if the sequence anx is Cauchy in x. Okay, we call an is Cauchy in X, Cauchy in strong sense. Okay, sequence AN is a Cauchy in strong sense if ANX. ANX means in range. Range is also is a subset of X. Therefore, ANX is a Cauchy sequence in X. Okay, and we have another result. There is a statement only, and there is no need of to prove this result. Okay, if AN is Cauchy in strong sense, then there exists A belongs to LX such that AN converges to A strongly. Okay, if AN is a Cauchy sequence in X such that Cauchy in strong sense, then clearly there exists A belongs to LX such that AN converges to A strongly. Okay, so we have AN Cauchy. Okay, and then AN is a Cauchy sequence implies AN converges to, you can find A belongs to LX such that AN converges to A strongly. Clear? Now we are going to prove one problem, and the statement of the problem is strong convergence is weaker than the norm convergence. Now what is actually the meaning of that? Strong convergence is weaker than norm convergence means every norm convergence implies strong convergence, but every strongly convergence need not imply norm convergence. Okay, so here suppose AN here we are going to prove AN converges to A uniform convergence, norm convergence, and we have to prove AN converges to A strongly. Okay, conversely we have to prove norm convergence implies strong convergence. Strong convergence need not imply norm convergence. This is what we are going to prove. Okay, so first one, suppose AN converges to A, then we are going to prove AN converges to A strongly. Okay, to prove AN converges to A strongly, we have to prove ANX converges to AX for every X belongs to X. Okay, so we have AN converges to A in norm. Therefore, norm of AN minus A tends to 0 as n tends to infinity. Now, norm of ANX minus AX you can write as norm of AN minus A X, and this is equal to norm of AN minus A into norm of X. And this tends to 0 as n tends to infinity. Okay, this is less than or equal to. Okay, this is less than or equal. This and the right hand side tends to 0 as n tends to infinity. This result. Okay, this implies norm of ANX minus AX tends to 0 as n tends to infinity. This implies ANX converges to AX. Okay, as X is arbitrary, we can say ANX converges to AX for every X belongs to X. This implies AN converges to A strongly. Okay, now for the converse part, we have to prove that strong convergence need not imply weak norm convergence. That means here we want to show that we show this by an example. Here we are considering some sequence, okay, and such that sequence such that ANX converges to AX. Okay, that means AN converges to A strongly, but a norm of A not but AN not converges to A in norm. Okay, and that example we will discuss later. Okay, and the last one, weak convergence. Okay, here we are saying AN converges weakly to A if for every X belongs to X and for every f belongs to x star, f of an x converges to f of ax. Then we call an converges to a weakly, and we write an converges to a weakly. Okay, this is true. An converges to a weakly for every x belongs to x, and for every f belongs to x star, f of anx converges to f of ax. Okay, then in the notation is an converges to a, here w. Okay, now we are going to show weakly convergence need not imply strongly convergence. Okay, we are going to prove weak convergence need not imply strong convergence. Okay, so we show this by an example. So weak convergence means an converges to a weakly if for every x belongs to x and f belongs to x star, f of anx converges to f of x. Okay. Now what about strong convergence? An converges to a strongly if for every x belongs to x, anx converges to ax. This is our strong convergence, and here we are going to prove anx not we are going to give an example of a sequence such that an converges to a weakly but an not converges to a strongly. Okay, for this consider the space L2. So we are considering example in L2. Okay, L2 consists of sequence A1, A2, etc. And here we are going to consider the operator shift operator, and we have discussed let T be an operator on L2 such that T of x equal to T of, suppose this is equal to x and Tx is equal to 0, A1, A2, etc. shift operator, and we have proved norm of Tx is equal to norm of x. Okay, and here we are considering A as a shift operator. That means for x belongs to L2, Ax is equal to, suppose x is equal to A1, A2, etc. Then Ax is equal to 0, A1, A2, etc. Okay, this is the shift operator. So clearly norm of Ax is equal to norm of x. This we already proved this. Okay, now what about a square x? What about a square x? Ax is 0. Okay, a square means a repeated 2 times. That means a of ax, and this is equal to a of 0, that's equal to 0, 0, a1, a2, etc. Okay, an, etc. Now what about a cube x? 0 3 times, a1, a2, etc. Now what about an x? 0, 0, etc. 0, this n times. Then a1, a2, etc. anx. Okay, we get anx is equal to 0, 0, 0, etc. 0 here n times a1, a2, a3, etc. Okay, where x is equal to a1, a2, a3, etc. Okay, now what about x? X you can write as actually sigma I is equal to 1 to infinity ai ei. Ei means e1 100, e2 01 x00, etc. Okay, ai. Now what about linear functional? Any f belongs to L2 star, L2. Okay, why? If x f belongs to L2 star, L2 star is LP star is LQ. Okay, here L2 star is LQ is same as L2, therefore f is also belongs to L2. So any linear functional on L2 is of the form we know. Suppose if you take x is equal to a1, a2, etc., an, then the next step, just to recall the definition of linear functional in LP. Okay, you take some b equal to b1, b2, etc., bn, etc., bn, etc. In L, if you take x in LP, this b must be in LQ. Here as p equal to 2, q is also equal to 2. Therefore, f is also of the form sigma I equal to 1 to infinity. This is actually bi. Okay. F of x is of the form sigma I equal to 1 to infinity bi ai. This is our linear functional. Okay, f is equal to this one, and you can write this as sigma I equal to 1 to infinity bi ei. Okay. Any linear function you can equate as an element in LQ. Okay. So this already we have defined f of x equal to this one. Okay. So any linear functional f and any x belongs to x. What about actually f of a raised to nx? What is this? This is actually sigma I equal to 1 to infinity bia. Therefore, it's actually b1 into 0 plus b2 into 0 plus etc. plus bn into 0 plus bn plus 1 into a1 plus bn plus 2 into a2 plus etc. And this is equal to sigma I varies from n plus 1 to infinity bi a I minus n. Okay. F of a raised to n is equal to sigma I varies from 1 to infinity bi a I minus 1. Because I phi equal to n plus 1, this become 1. Okay. Now what about norm of fn x? Norm of f of a raised to n, actually modulus of this is equal to modulus of sigma I equal to n plus 1 to infinity bi a I minus n, and this is less than or equal to sigma I equal to n plus 1 to infinity modulus of bi a I minus n. Okay, and we can apply our result, and this is equal to, this is actually less than or equal to sigma I varies from 1 to infinity mod ai whole square whole raised to 1 by 2 sigma I equal to n plus 1 to infinity mod bi whole square whole raised to 1 by 2. Okay, so if you consider as n tends to infinity, this term tends to 0. Okay, that means f of a raised to n x actually tends to, f is a linear function, therefore we can write f of 0 equal to 0, therefore we can write like this. Therefore, for every f belongs to L2 star, f of a raised to nx converges to f of 0. This implies an converges to a weakly. Okay, so we have anx is 0, 0, 0, n times a1, a2, etc. Okay, if n tends to infinity, we get 0, 0, 0, 0, etc., 0, 0, 0. Okay, therefore we can easily say that f of a raised to nx tends to, actually this is equal to tends to 0, and 0 you can write as f of 0. Okay, therefore an converges to a weakly. But what we have? We have norm of ax is equal to norm of x. We have this result. Okay, but what about norm of a square x? Norm of a square x equal to norm of a of ax. Okay, and this is equal to norm of ax is same as ax equal to 1, norm of a square x equal to norm of a of ax, and that's equal to norm of ax is norm of x. Therefore, norm of ax is norm of ax, okay, and norm of ax is norm of x. Proceeding like this, we get norm of a raised to nx equal to norm of x. Therefore, this implies norm of a raised, thus we get norm of a raised to nx equal to norm of x. Therefore, clearly a raised to nx now tends to 0 for every x. Okay. This implies an not converges to a strongly. Okay. An not converges to that means here a raised to n x, that is we get norm of anx equal to norm of x. This implies anx not converges to 0, because this is possible only if x is equal to 0. Okay, therefore norm anx not converges to 0. This implies an is not strongly converges to 0. Okay, this implies weak convergence need not implies strong convergence. Okay, just revise what we have discussed today. Okay, today we have discussed different types of convergence in L of x. First one is norm convergence. Okay, uniform convergence, that is our usual convergence. An converges to A. And the second one is strong convergence. An converges to A strongly, yes, if Anx converges to Ax. Okay, for every x belongs to x. Now the last one is weak convergence. An converges to A weakly if f of Anx converges to f of ax for every f belongs to x star, and this is also true for every x belongs to x. And we have proved two results. Weak convergence need not imply strong convergence. Also non-convergence implies strong convergence, but strong convergence need not imply non-convergence. That we have to prove. Okay, we prove that using one example, and that example we will discuss in our next class. Okay.